So the video quality is not the best there, but you don't need to see my face anyway up here. So the next thing I want to cover is the derivation of Vets Law. Skipping around, nothing like that. And this is something we covered a little bit in 102, but didn't really dig into the math much. And I figured, here we are in a 200 level class, and it's time to dig into the math and understand this a little more fundamentally. Now, if you remember, you probably remember Carnot's efficiency. You remember Carnot from 101? Basically said that and I'm just going to throw it out here just as kind of a mnemonic, because what I hope when you leave the energy technology program, that you don't have a whole bunch of jumbled up mixed match facts and figures to try to memorize. I'm hoping that when you sit down, you realize that the Vets Law derivation is actually an efficiency equation, an efficiency law, and and that should be filed in the same part of your brain as the Carnot efficiency. But they're very different, but you should be able to, when you look at any new problem, regardless of the energy, you should be able to put it into some kind of category. Is this a Carnot problem? Is this a Vets problem? What is it? But I'm just going to throw Carnot off here to the side, just as a reminder, because the symbol is eta, and I didn't draw that one very well. Eta kind of looks like an N, kind of looks like an H, but what I do is I usually give it a little curly, and then it's important that this part comes below the line, just kind of like the difference between a Q and an A. So it's the letter eta, stands for efficiency. Why it looks like an N, I don't know. Instead of an E, E's epsilon. But if in Microsoft Word you're ever typing this, you type in the letter H and then turn into a symbol. So if you're looking, so the symbol font in Word will give you the Greek letters. So this is an H. In Carnot, though, what you're looking at is the high temperature minus the low temperature over the high temperature. And what this is telling you from Carnot is that the hotter something gets, the more efficient it's going to be. And if you can't remember what's on the top and what's on the bottom, just go back and remember the third law of thermodynamics, and you know that you can never hit absolute zero. So you can never have the low temperature be down in the denominator. Because if it was, it might be zero, and you'd have infinite efficiency. And another thing is, you also always know that efficiency is greater than 0 and less than 1. Also critical. Okay, so there's Carnot. Now let's look at Vets. So what Vets did is he just did a little thought experiment with you, if you will, and thought of a turbine is sort of just an idealized cylinder, and it's a cylinder turned on its side, and the cylinder itself really has no thickness whatsoever. So from this side to this side is approximately 0. Now you're like, okay, well that's not realistic. But on the other hand, if you're just a little air molecule, here you are, you're just a little oxygen molecule, or maybe you're a nitrogen molecule flying through here. The question is, where's the front of the turbine and where's the back? Well, the front's in front of the middle and the back's behind the middle. And then you're like, well, where's the middle? Well, it's got to have a middle somewhere. And the thing that we're going to work on, though, is we're going to have some velocity going in. And actually, I'm going to go to the Wikipedia derivation for a second. Wikipedia, BETZ, Vets Law. Okay. So what they're going to use here, and I'll just use the same convention, is that there's a upstream velocity and a downstream velocity. We're just going to call the upstream V1 and the downstream V2. So he's got some V1. I think what we'll see here. And then you've got some V2. Now, this should be an obvious question, but which of these two velocities is greater, V1 or V2? It better be V1. Similar to the Carnot, similar to the Carnot equation. You got a hot side and a cold side. In the wind turbine, you got a fast side and a slow side. Well, what happened? Why is V2 smaller than V1? So yeah, it's got less energy. And where to go? Well, it went into the turbine, went into the generator. Okay, so that's all very obvious. Now, but in the middle here, you've got some V. I'm just going to put V bar. The Wikipedia put V average, but anyway, V bar, V average, same difference. Maybe I'll just write them both. V bar equals V average. Doesn't matter. And so again, going back to that little air molecule moving through, it sort of doesn't really matter what the velocity in here is, but we can all agree that it's got some average. The same thing is true. In this V1 up front, there's not just one exact V1 either. All these molecules, some are going forward, some are going backwards. So really this V1 is sort of, and I'm not going to put the bar over it, but it is the average velocity of that wind. And over here it is the average velocity of this wind. Another thing to keep in mind, is velocity a scalar or a vector? Velocity is a vector. It's got a direction. Temperature is a scalar. It doesn't. So another thing to keep in mind is, this velocity, really the only component of the velocity that we care about, that we're doing anything about, is the purely horizontal component. Now, is there going to be a side-to-side component? Sure. Is there going to be a vertical component? Sure. But the only part that's really going to do us any good is the part that's moving straight through the turbine. So we've taken, what really is a three-dimensional problem and turned it into a one-dimensional problem. You get that? So we're kind of treating velocity like a scalar, even though it's a vector. That's also very, very important to think about. When you get into, more advanced modeling, say you take a couple CAD classes and start doing some heat transfer and things like that, it's very, very important from the very beginning to simplify your problem as much as possible and say, gosh, can I turn this into a one-dimensional problem? Same thing with like heat transfer going through a wall. Do I really need to know how much heat's going up, down, sideways? No, you just want to know how much is going through. You intentionally turn it into a one-dimensional problem, because then you're going to have, one or two equations and just a few unknowns rather than this giant mess that you have to deal with. So, next step here. So I think I've explained that you've got an upstream velocity, a downstream velocity. Somewhere in the middle there has to be the average. The other thing to keep in mind is, could this downstream velocity ever be zero? Why couldn't it be zero? Yeah, because where would it go? You'd have 100% efficiency. Yeah, or the air would have to just be consumed by the turbine somehow, or it would have to be completely deflected. Thinking back to our vector problem, and you keep hearing these rumors. Oh, somebody beats Vets Law. Somebody beat Vets Law. Well, maybe, I don't know, but it would be difficult to imagine a turbine where there was zero. well, let's just call this, let's just call this direction the x direction, and call this the r direction, and then we can call the other one the theta direction. Remember polar coordinates from 102? So wind turbine, much better to phrase this thing in polar coordinates rather than Cartesian. So we've got an x, an r, which just points out in every direction, and then theta, which points around the circumference. So theta is the circumferential direction. We still got x, y, and z locally. You can see that this little curved arrow is still going to be perpendicular to r, regardless of which r we're talking about. It just points out, and that out direction is always perpendicular to that circumference, which is the same as a tangent. You can think of it that way. So getting back again to this vector thing, we're only concerning ourselves with the x direction. You might conceive of a turbine where the wind comes in here and it just all gets pushed out to the sides, or maybe some of it comes in and does some kind of weird circumferential thing. But for now, let's just stick to the straight bets. Okay. That's the only thing where I could think that V2 actually might be 0. But other than that, you're like violating conservation of mass because the air molecules have to go somewhere. Okay. Good. Conservation of mass. There it is. You guys see that okay? Or maybe I'll make it maybe a little bigger. All right. Now, if you also remember 101, 102, I really tried to drive home this whole concept of what the dot over a symbol meant. You guys remember that at all? What the dot means? Yeah, it's the time derivative. And so let me write out exactly what m dot is. You don't have to know calculus to understand it, but here it is. M dot equals delta m over delta t, or, and so that delta is a change, or if you're talking calculus, you might write it this way, dm dt, and the delta just means a big change, the d means a little change, and the dot just means how quickly it's changing right now. And so it is, it's the mass flow rate. And so what you're looking at, if we go back to this guy, well, let's just grab this little chunk of matter here, right? Here's our little. I captured an oxygen molecule and a nitrogen molecule, and you'll notice I used the double bond for oxygen, triple bond for nitrogen. That is accurate, by the way. But this is our little m. And then, here comes one little m, here comes another one, here comes another one, and it's moving past us, and the faster it moves, the bigger the m dot, right? So if it's just sitting there, that's our m, but if it's actually moving, then that's your m dot. And the faster it moves, the bigger m dot is. And you can take it right back to your algebra. Here's T, here's M, and if you've got a slow wind, you're somewhere down here. If you've got a fast wind, you're somewhere up here. But this slope, this rise over run, there's your delta T, there's your delta M, how fast the mass is going by, and the slope is just m dot. That's all it is. Okay, now, m dot equals rho A1 V1. Let's look at that. M dot equals rho A1 V1. Now, again, very important skill here. Do your dimensional analysis. I can't really emphasize that enough. So let's just do the dimensional analysis right now to make sure that we understand that equation. So we already, and the only 3 dimensions we get to use are mass, length, and time. Don't have to worry about voltage or current or anything like that. So M dot, we already know, is mass divided by time. We know that density is mass divided by length cubed. We know that area is length squared, and we know that velocity is length per unit time. So all I did was take this equation that's going to help us derive Vets Law and verify that the dimensions work out. Okay, so let's make sure. The masses cancel, the times cancel, and effectively I've got length cubed in the numerator and length cubed in the denominator. And I get all warm and fuzzy knowing that the units work out. Okay, next one. Equals rho SV. V equals rho A2 V2. Now, one thing that the authors have assumed is that the density of the air does not change. It's not, this thing is not a compression. You know, it's not an engine. We're not really compressing air. Does the density change a little bit? Of course it does. If it did, the thing wouldn't be making any noise. You know, it is compressing air, but not. It's not like the air coming out the back end is any less dense on average than the stuff going the front end. A1, just for clarity, is whatever control volume goes to the front. And this is going to become important if you start trying to jam too many wind turbines in one space. Obviously, because they can't all use the same air multiple times. And then he's sort of drawn the back end as being slightly larger and a little more diffuse, but really it doesn't, those areas are not going to matter. This area, though, is the effective area of the turbine. This S is the effective area of the turbine. That's, you know, when you say, what's the diameter of the turbine? Boom, that's it. That's your S. That's the area of the turbine. Now, from there, what he's done is taken two separate equations. One is, what equation is that? What's F equals ma? Whose is that? Who came up with that bad boy? Newton. That's Newton's second law. So let's get going on that. F equals ma over here. And then the next one is just the power and work equation. We've beaten that one to death a bunch too. So let me write that guy out. Power equals. I'm going to try to do the Newton's equation in one column, and I'm going to try to do the power in the other column. I just want to make sure we've got this going in a place that makes sense. So P equals dE dt. Now we could have written this as E dot, right? Because we know that dE dt is the same as E dot, but nevertheless, same, all speaking the same language. Okay, so here's Newton on one side, and here's just the power on the other side. Okay, so from there, we know that acceleration is just a change in velocity with respect to time, dv dt. And again, this is how quickly the velocity of the air is changing through the turbine. That's your dv, and we know it's got to change. If it didn't change, we wouldn't get any energy out of it. And now he's pulled kind of a sneaky little trick, taken that dt and slipped it from under the v to under the m, which you might say, gosh, is that really allowed? Well, the answer is yes. He kind of treated this calculus equation a lot like you might treat an algebra equation, right? Because it doesn't matter, because you can see that you're multiplying m times dv, and if this were the number 2 under here instead of dt, you could divide the m by 2, or you could divide the dv by 2. Doesn't matter, you're going to get the same answer in the end. So slips that under there and just says equals m dot delta v. So playing a little free and loose with the deltas and the d's and the dots, but that's allowed. Now, we already know the formula for m dot. We wrote that a second ago. The delta v is just the change in velocity. That's just the fast speed minus the slow speed. And the m dot that he selected to use was the mass flow rate through the middle of the turbine. Okay, so let's write that out. Equals, so rho S V V1 minus V2. Okay, so hopefully we can see now where all this junk comes from. We know that the mass flow rate is, how dense it is, and this should make sense too. If the air is more dense, you're going to have a higher mass flow rate. If you got a bigger turbine, you're going to have a higher mass flow rate. If you got more velocity, you're going to have a higher mass flow rate. Multiply them together, that is the mass flow rate. Boom, right there. And then, so that's our rho SV, right there, our average. Now, the delta V, it's just what the change is, the high velocity minus the slow one. So that should be pretty straightforward for force. Now, let's hop over to power. And what we've done here, and I know I've stressed this before. I've told you that power is always equal to force times velocity. Now, one subtle thing that I must mention right now. We know that velocity is a vector. I think you probably also know that force is a vector. So force has 3 numbers, velocity also has 3 numbers. Typically, when you see a little dot like that, you're used to multiplying, and you're used to multiplying scalars by each other. 20 times 10, x times y, et cetera, et cetera. This little dot is actually what's known as the dot product. It's a special symbol for multiplying 2 vectors together. It doesn't say so, but that's exactly what that dot is. It's the dot product. And what that means, and I'm not going to get into all of it, but if you want to research it on your own, you can look at the dot product. What it means is it takes these 2 vectors and produces a scalar. It takes two numbers. So maybe I'll just write it out here as a little side. What you've got an F1, an F2, and an F3. And what we're actually doing is multiplying each of the forces by each of the velocities. Because remember, I told you that velocity is a vector, and there are 3 dimensions. So what you come up with when you're done is power, and power is a scalar. When you talk about power, it doesn't have a direction. So that's the dot product. The only one we're worried about is in the direction of the wind. That's the only one that's going to make the turbine spin, but just a little subtlety there so you're not misled. All right. Now, substituting the force computed above into the power equation will yield the power extracted from the wind. So we've got, so right there we've got an equation for force. So really all we're going to do is take what we just calculated on the left side here and run it through the power equation. The only thing that changes is we're going to square that V, right? Because there's our force multiplied by the V. So equals rho S V squared V1 minus V2. That's power. Okay. Now the rest of this becomes a little, and I don't want to go. The rest of this I'm not sure I really have time to delve that much into, but I'll just scroll through the highlights of what's on this website, and I've used this in the past, and it is pretty well written. Okay. So what he does is says, however, power can be computed another way by using the kinetic energy. And so we see that. We've got P equals delta E over T. So all he's done is taken the energy equation, and we already used that one a second ago, right? The 1/2 mv squared, and that's why I thought it'd be a good idea to just go right into bets here. So the change in energy is 1/2, well, let's just do the steps here. So P equals delta E over delta T equals basically E1 minus E2 equals over delta T, right? So not big T, little t. Use a little t for time, use a big T for temperature. So that's your 1/2 m v1 squared minus 1/2 m v2 squared over delta t equals 1/2 m dot v1 squared minus 1/2 m dot v2 squared equals 1/2 m dot v1 squared minus v2 squared. Boom, right there. And then again, we go back and we can write that, and we know what m dot is, so that's 1/2 equals 1/2 rho s v v1 squared minus v2 squared.
How'd you get rid of the time? Oh, is that just the dot? You just put the dot in?
Yeah, the delta t just got absorbed into the dot.
Okay.
Yeah. Easy to miss because it's such a, I don't think you can make a much smaller symbol than the dot. But that's where it went. Yeah, good point. Okay, now, what he says is, both of the expressions for power are completely valid. One was derived by examining the incremental work done, and the other one by conservation of energy. From there, we just set them equal to each other. I can just copy paste this guy. Let me see if I can lasso it. I don't know. Wow, look at that. See if I can drag that baby down here. Come on, laptop. Not too bad. Okay, so now I've got two things. Sorry, that didn't end up exactly the right place. We've got rho s v squared v1 minus v2 equals 1/2 rho s v1 squared minus v2 squared. So, and that's kind of the way to use math to your advantage, just like corner the variables. They look same, but different. Now, just going through and just solving that algebraically, this is the beautiful thing that pops up. And it's it should be almost obvious when you look at it, but what does that very last equation on this page say?
Velocity equals 1/2 of the difference between the incoming velocity and the outgoing velocity?
Yeah, but if you're going to just describe that to somebody without using, you can't use the word plus, you can't use the word half, you can't use the word equals. Just describe it to somebody else. It's just, exactly. It's the average velocity. And you might say, duh. but between the high velocity going in and the low velocity going out, the velocity in the middle should be the average. I mean, we just spent, I don't know, 20 minutes farting around with algebra to realize, oh yeah, this, where the heck am I here? This poor chunk of matter that we started out with, by the time it's, gone through the ringer, bounced around here, there, and everywhere. Oops. Somewhere between.
He got his picture in the book.
What's that?
What the heck? He got his picture in a textbook.
Yeah. There's another subtle step that's coming up that's not quite as obvious, but you say, yeah, somewhere between fast and slow is just right and just average. So that's kind of the upshot. So V equals 1/2 V1 plus V2. Now, what Vets does from here, and I'm not going to write the rest of it out because there's a little bit of subtlety here. It says returning to the previous expression for power based on kinetic energy. What he's done is just sort of expanded this whole thing. So you've got your V1 squared minus your V2 squared. Another way of writing that is, well, just like so. If you were to sort of take this thing and work yourself backwards, this is just another way of writing it. And you'll notice that energy, so E dot is also just power. And this is the tricky part. I don't expect you to necessarily understand this. This is something to just kind of maybe take home and digest a little bit. But differentiating the power with respect to the ratio of the two velocities. So really all he's done here is come back and say, I don't really care that much about what the velocity is. I don't care if it's 10 miles an hour, 20 miles an hour, 3.5 meters per second, 30 meters per second. It doesn't really matter. What matters more is the ratio of the two velocities. Doesn't, like, the units don't matter that much. It's really the ratio that's a bigger deal. Is the velocity going in 10 times more than what's going out? Is it half? So you're sort of, and another way of looking at that is normalizing. I don't know if have you heard the word normalizing before? Normalizing is a fancy word for dividing by. And all we've done here is normalized the slow velocity by the fast velocity. And we can just sort of say, for the sake of argument, the fast velocity, which is V1, it could just be 1. I mean, the units don't matter, the dimensions, we'll just call it 1. Like right now, we're just going to agree to whatever the wind speed out there is right now, it's 1. And you can make up whatever units you want. And we know that V2 is going to be smaller than 1. And so now the beauty of it is you're always operating, you're only using the numbers between 0 and 1. It doesn't get all weird with numbers. So what he's done is I've got some ratio between the slow speed and the fast speed, and that's really all I care about. And it's just and that is almost like taking those two variables and then just turning them into a single variable. It's just a new variable that we've agreed to. It's just the ratio, and we could even just get rid of V2 by V1 and just call it A, whatever, or R for ratio, whatever the heck you want to call it. So this function, I think we can both agree, is something that you can plot. Remember back to NRG 101 and 102 when you plotted a parabolic model for population. That's a parabola. And when you take the derivative of something, all you're doing is looking at its slope. So for example, if I had a a function that just looked like this. Y equals mx plus b, and I took the derivative, and here I know that, this slope is m, this guy is x over here, this guy is y. If I take the derivative of that, it's just looking at what the slope is. And what's the slope? Well, it's m. Pretty easy. I just took the derivative. It's constant. So this is now x, and this is now dy dx. I took the derivative of y with respect to x, and there it is. It's just the value m. It's a little weirder when you got curves and things like that, but I think you get the point. So when you do that, when you take the derivative, you end up with this function right here. And obviously it has a maximum. And we've even used this to look at the power curves for motors in 299. At some point, you've got a maximum power performance of your motor. Same thing here. This thing has a maximum power. Where is it? Well, it's where the derivative is 0. Boom, right there. And so what comes out is this very simple fraction. It's 16/27. And if I do that calculation, 16 divided by 27 equals 59.2. I was about to say that Vets limit was 57. It's close. It was another odd number in the high 50s. 59. So that's Vets limit right there. That's the theoretical maximum efficiency that you can ever get out of a wind turbine. Let's just wrap it up here. It says, at first glance, a little hard to understand. 59.3, blah, blah, blah. Says the model breaks down at very low exit speeds. Obviously, we assume a constant density. We said that already. It implies the cross-sectional area. Yeah, we don't need to worry about that. I guess, well, it says at V2 equals 0, the cross-sectional area is infinite, and in a sense, that smacks of what I drew. If the V2 were 0, it would mean that all of this wind was in fact coming out somewhere else, right? So we mentioned that already. So is that pretty clear though, guys? I mean, where the whole thing comes from, Vets Law? Well, you can't really beat it. I mean, unless you redefine the conservation of energy, or redefine Newton's second law. Vets Law is just as solid as Newton and the first law of thermodynamics. That's what we based the proof on. Okay, so let's take a break there. Any questions at all on Vets derivation? I mean, I know there's a little bit of math going on, but really we did all the algebra up to that point. I kind of did a little smoke and mirrors near the end when the calculus came in and we took the derivative of this curve. But anyway, that's where it is. Do you have a question there, Corey, on it?
It was just one question when we were running through the power.
Sure. Yeah.
Where we have 1/2 the density of S V squared.
Yeah.
V1 minus V2.
Yeah.
How do we get to, why is the velocity squared?
In the power right here? In this guy right here?
Yes.
Okay.
And when you ran through it and broke that down,
Yeah.
Why do you square the velocity instead of putting the square past the parentheses?
Okay, sure. So let's just back up to right here. Maybe I'll get a different lighter. So I think we can all agree that power equals energy divided by time. No questions there. Another thing, and I think I've talked about this in the capstone, power whether it's mechanical power or electrical power, it's always an across variable times a through variable. And in this case, the across variable is force, and the through variable is velocity. If we were talking electrical circuits, the across variable would be voltage, and the through variable would be current. But it's always an across times a through. Force is the across, velocity is the through. So that's just the definition of mechanical power in this case. So now, over here, on the Newton side of things, we're not going to argue with F equals ma. Acceleration is just change in velocity with respect to time. Here we kind of snuck that dt under there. I already showed you that. And we'd already defined what m dot was. We agreed that m dot is rho SV. And so the delta V is just the change in velocities that's there. The only sleight of hand, if you will, we just took this whole thing, which was F equals rho SV. And remember, that V is the average velocity in the turbine, whatever that happens to be. And you know, we already know that's going to be the average in the end. So I just took rho SV with V1 minus V2 and multiplied it by V. Whoops. So that V has to go right there and turn into V squared.
Okay.
You see?
Now, when we went through it below on the next page down.
Yeah.
So we've got.
I just grabbed it.
V1 and V2, but they're both squared in the parentheses.
These guys are, yes.
Yes, so what happens there? I mean, why?
Oh, yeah. Hang on. Jeez, come on. Well, I got the itchy trigger finger on this thing for some reason. I'm not touching. I'm not, I'm not breathing. I think I've got. I know what the problem is. So right here we set these two sides equal, and I think you can see that the rho vanishes, the s vanishes, the let's just do this thing. Let's just do a new page down here. V1 squared minus V2 squared equals, let's just do it this way, V1 plus V2 V1 minus V2. Let's see if we get this right. So that's V1 squared minus V1 V2 plus V1 V2 minus V2 squared. So you can see that this guy and this guy cancel, leaving us V1 squared minus V2 squared. Is that the expansion you were looking for? Because that is a step getting from setting these two sides equal to getting back down to this average.
Okay.
That was something I kind of skipped, just an algebraic step that I skipped over.
Oh, I thought that we took that square and put it to the V, like to the V in front of the parentheses. You can't do that, right?
Well, no, absolutely
okay,
not.
okay.
No,
That's
absolutely
what
not.
was
No,
confusing.
yeah. No, so I guess there were two separate questions there. One was, where did this little V squared come
Yeah,
from? And I
that
think I
makes
explained
sense.
that.
Yeah.
But then in terms of getting back down, hopping from this guy all the way to here, we just invoked this distributive property there. That's just kind of algebra 101. So, okay, cool. Well, let's take a break there. And I think hopefully 15 minutes is enough time to get us going on Bernoulli's equation. So that's an important one right there.